Okay, we are going to cover coffee cup calorimetry. And, it doesn't have to be in a coffee cup. We just tend to use coffee cup because they're well insulated. We used to use styrofoam coffee cups, but in an effort to be more sustainable, we threw all those away and bought some plastic ones. So anyway, that's what you would have been doing in lab this week. But what I'm going to do is basically go over a problem very similar to what you experience in lab and what you might see on the exam, obviously. So let's start off with our reaction. Okay, and we're measuring, in this example, we're going to measure the amount of heat produced in a particular reaction. So the reaction we're going to do is HCl AQ plus NaOH AQ, and we get H2O liquid plus NaCl aqueous. And there's our reaction. Hydrochloric acid plus sodium hydroxide gives us water and sodium chloride. So the setup, we would have two containers, one containing hydrochloric acid, and this is 50.0 mLs of 1.0 molar HCl. And I'm just making up numbers. Starts at 20 degrees Celsius. Here we have 50, whoops, I forgot to put the little squiggly lines that let you know that it's a liquid. Anyway, 50.0 mils of 1.0 molar NaOH. All right. And this also is at 20.0 degrees Celsius. Now we are going to combine those. And we are going to combine them in our coffee cup calorimeter. And this looks nothing like a coffee cup. Okay, but I'm just showing you that it's like a thick styrofoam or some other sort of insulated cup. So what we are assuming here is that no heat is transferring in or out. Okay, we're assuming that does not occur. Good assumption, bad assumption. Within our ability to measure things, it's a reasonable assumption. So when we combine those, we end up with 100.0 milliliters of water and salt. So they're the HCl and the NaOH in the two beakers. To start with, they're in a 1-to-1 stoichiometric ratio already. There's equal number of moles of HCl and NaOH. So when we combine them, neither one is in excess. And so over here in our coffee cup, there is no excess HCl or NaOH. And we measure the temperature go up to 26.9 degrees Celsius. Okay. So, I forgot to write up here that the whole point of this is to find delta H. Delta H equals what? All right. So what is our system? What is our surroundings? The system, simply put, is the reaction. And that's almost always the case in chemistry. We're interested in the reactions. The surroundings is the water. And when you do it in lab, it's going to be the water and the coffee cup. Okay. But for our purposes here, we're just assuming it's the water. And that is to say the NaCl solution that's in the coffee cup when we're all done. All right. So what we do know is that heat is lost by the system, that is to say the reaction, and gained by the surroundings. That is to say, the water. How do we know that? Simply put, is because the temperature went from 20.0 degrees Celsius to 26.9. The temperature goes up, the water must have gained heat. Where did that heat come from? It came from the reaction. Okay? So that equation that we used before that was super confusing, I said it was confusing. Sometimes Q system plus Q of the surroundings is equal to 0. And we can say Q of the reaction plus Q of the H2O is equal to 0. Okay? So now all we got to do is calculate Q of H2O. We're going to find that and then use that to solve for that. Okay? You'll see what I mean in a second. So Q of H2O, simple, is mass of the H2O times C of the H2O times delta T of the H2O. Okay? Mass of the water. Well, let's go back up. What's our mass of the water? If we assume that the density of water is 1 gram per milliliter, and we assume this is a fairly dilute solution, we can say that we have 100.0 grams of water. And that's what we do assume. So we have 100.0 grams of water. C of the water never changes, 4.184 joules per gram degree Celsius. And you might see it as 4.18, just sig figs, no big deal. And then delta T of the water, 26.9 degrees Celsius minus 20.0 degrees Celsius. Both those beakers were at 20 degrees Celsius, the HCl and the NaOH. So that is our initial temperature. Okay? Do the math on that, and we come out with 4.2 joules. Okay, is that a reasonable amount of energy? Well, it's pretty hard to say, but one thing we can say is that we have a positive, and that's a positive value because the water gained heat. That makes sense. The water gained heat, so it has a positive Q value. Now we know that Q of the reaction plus Q of H2O is equal to 0. Well, that means Q of the reaction is equal to negative Q of H2O. So what does that mean? Q of the reaction is negative 2884.2 joules. Okay, so that was the heat produced in that particular reaction. Now we want to generalize it out to delta H, and that's what delta H is. It's really just a general way to say that reaction of HCl plus NaOH evolves this amount of heat per mole. And when we do these for acid-base reactions, the convention is to get them per mole of H2O. So what we're going to do is we're going to do Q of the reaction per 1 mole H2O produced. Okay, so we just take our Q of the reaction, which is negative 2884.2 joules, divided by 0.0500 liters of HCl times 1 molar HCl. Oops, that's supposed to be 1.0 molar. That really only makes a difference for sig figs, but let's fix it. And that tells us how many moles of water are produced. Actually, we should probably have one more term in here, just to be technically correct. 1 mole H2O per 1 mole HCl. There we go. Now it's perfect. Okay, and that gives us a value of negative 5.7684 joules per mole. And I'm going to just convert that to kilojoules because these values are usually reported in kilojoules, negative 57.7 kilojoules per mole. And I didn't pay too much attention to sig figs. We could go back and calculate it all out. Maybe it should be negative 58. That'd probably be better sig figs. Negative 58 kilojoules based on that value of 1.0 molar HCl. So 2 sig figs probably is better. We don't have a high level of precision, which is why it's okay to do this in a coffee cup and make a few assumptions. Anyway, that's calorimetry. I hope that helps.